My name is Rikith Reddy. I'm a software engineer at Arista Networks. In today's talk, I'll be talking about one of our project, WebQoE. WebQoE stands for Web Applications Quality of Experience. This project mainly focuses on quantifying the user's experience in a Wi-Fi network. We do that by trying to understand the user's application performance. Before we dive into this algorithm, let's see why estimating an application's quality of experience is actually important. Say somebody asks you, what is the quality of experience of a particular user in your network? If you went by a traditional approach, you would check the packet latency, the user's throughput, his radio link quality, such as RSI, SNR, and retry rate. However, mapping these parameters to a subjective user experience can be quite challenging. So, how does the user perceive the quality of experience of your network? The general user's perception of the network depends upon the application is using. For example, if the user is having a Skype call, the quality of his call determines how he feels about the network. Similarly, if he's using Google Docs, the responsiveness of Google Docs is what would make the user's impression of the network. So we can infer that the subjective experience can be obtained by the user's experience of that application. So it comes to a question where can our network detect if a particular user is facing a good or bad experience for a particular application? We at Arista have been working on this problem for the past couple of years. One of our earlier solutions had a self-learning network, which estimated the call quality of video and voice conferencing applications such as Skype. Here is a brief summary of that method we used. In the first phase, we just detect the call on the access point, and for every 30 seconds, we try to measure parameters such as bitrate mean, bitrate standard deviation, packet rate mean, and packet rate standard deviation. These are then fed to a classification model, which classifies whether that particular 30-second section was good or bad. We use this information and develop key insights on a server, like number of affected clients for that particular application and the bad usage time for that application. This solution could not be expanded to support other applications. It only supported VoIP and video conferencing applications. The major limitation there was that it required a continuous flow of packets. And if you look at the highest volume of traffic on the internet today, it is web-based. And web traffic is bursty in nature. So bitrate and packet rate will not give much information about that particular application. This calls us for designing a new method to estimate the quality of experience of web-based applications. So we did that. We collected few samples of good and bad experiences in the network, and we started analyzing them. Upon analysis, we found that most of this traffic was TCP. So we went a step further and tried to analyze how do those TCP traces look. What we found was one of the most prominent characteristics of traces with bad experience was packet retransmissions. Packet retransmissions in a TCP connection occur due to a prior packet loss in the network. This happens because TCP is a reliable protocol and all packets sent from one end need to be received at the other. We also observed that that the TCP connection spends in a wait state whenever a packet retransmission event occurs. So our idea was to use these packet retransmissions to compute the user's quality of experience. In the beginning, we tried to just count the number of packet retransmissions happening over a TCP connection. However, that seemed a little unreliable because TCP has its own optimization for fast retransmissions where the retransmission time is very low, making the wait time also very low. So later after checking more about how TCP works and how its state machine works, we finally decided to start tracking the start and end of the packet retransmission events. So that's what we did. We tried to simulate a very simplified version of the TCP state machine on the access point, which could detect the retransmission events and thereby computing the amount of time the TCP flow spent in a wait state due to potential packet loss in the network. So this laid the foundation for the algorithm I'm going to discuss. The algorithm is pretty straightforward, so explaining by an example is the best way to go about it. Here is something I'll be using throughout the example. So this is a very simplified version of a data packet you would see in the network. So I'll be just using the sequence number, the ACK number, and the payload size. All these three are present for any TCP packet you might see. The first two fields, the sequence number and ACK number, these both are used by TCP to achieve a reliable connection, where sequence number is the marker of the first bit that is being sent over the TCP connection. ACK number indicates how many bytes of data have been received by the host sending that packet till that point of time. Payload is straightforward, where it is the amount of data that is being sent over the TCP connection. TCP's logic here being that if a host receives this packet from the other end, he is expected to send back an ACK number, which is equals to the sequence number plus the payload size of the received packet. So going back to our example, let's say we have a client who is trying to fetch some data from the server. So TCP being a reliable connection requires an acknowledgement for every packet that is being sent. However, you might realize that if you send a packet and wait for the acknowledgement and then send another packet, this will cause unnecessary delays. To avoid this, TCP uses something called as windowing, where it can send out a bunch of packets without expecting an acknowledgement for them. The number of these packets is dictated by a variable called as window size. So for our example, let's say we have a window size of 5 and the server is trying to send all the data in that window. For simplicity, I just kept the payload size as 1 to help you understand what would go on. So let's say the server sends in its first packet and we see that packet at T1 on the access point. The client, on receiving this packet, should acknowledge this packet. So we can expect an acknowledgement number of 1 plus 1, that is 1 is a sequence number and 1 is the payload size. So he will be sending back a packet with ACK number equal to 2. And for this example, the payload size is 0. So this is just a simple acknowledgement packet that is being sent from the client to the server saying that it has received the first packet. You can just ignore the sequence number field for the client, because for this example, we won't be showing the client sending any data to the server. So after this, the server continues. It sends in its next packet that is of sequence number 2 and payload size of 1. Upon receiving this, the client is expected to send back an ACK of 3, which it does. So let's say after this point, the server sends in its third packet, which gets lost in its network. So we can note, please note that server has no way of knowing at this point of time that the packet has been lost somewhere in the network. So it just moves ahead in its TCP window and sends in the next packet. Upon receiving this packet, what does the client do? So previously the client had sent in an ACK number of 3. So that implies it is expecting a packet with a sequence number of 3. However, you can see that it has received a sequence number of 4, which is not expected. At this point, TCP dictates that you just send in the last acknowledgement for which the data had been received intact, that is ACK number of 3. So you send back the same ACK number again, that is 3. And as you can see, these both acknowledgement numbers are same on the network if you look at from the access points point of view at T4 and T6. So this is what we call a duplicate ACK in a TCP transmission. And you can observe that this duplicate ACK was actually triggered due to a packet loss. So if you go back to the slide where I was talking about detecting the start event of a packet loss, that is a packet retransmission, what exactly triggered a packet retransmission? Packet retransmission was triggered by a packet loss in the network, but we can only detect this duplicate ACK, which we can use as an indicator for the detection of the packet loss. So let's say we just keep a note of this point where we first saw a duplicate ACK, inferring that there was a packet loss in the network. Going ahead with the communication, the server sends in its last packet as well, that is received by the client. And as expected, the client will be sending another duplicate ACK because it still did not receive that third packet, that is a packet with sequence number 3. You will find another duplicate ACK here. At this point, we see that the server is waiting for an ACK number of 6, that is for the last packet it has sent in on the network, that is of sequence number 5 and a payload size of 1, but it has only received ACK number for 3. So there's a certain timeout called the TCP timeout, after which a packet retransmission is triggered, where the server infers that the packet with sequence number 3 might have been lost in the network, so it just retransmits that packet. So this is the same retransmission we had been seeing in our traces for bad connection, and that was occurring due to packet losses in the network. And after receiving this packet, the client acknowledges for all the data it had received till now, that is for the last packet it had received. So at this point, you can see that the AP knows that there had been a packet loss because of a duplicate ACK at time T6. And at time T10, the duplicate ACK is no longer being sent. So from this information, we can conclude that the lost packet has been somehow retransmitted back to the client. So we can just compute the time lost or the time TCP spent in a wait state due to packet loss as T10 minus T6. That is this particular section which I marked with red. So what does the AP look at? So how will the AP look at? It is pretty straightforward. As I mentioned, all you need to do is keep a track of what was the last acknowledgement you have seen on your network. So what we do for that is we try to maintain states for two directions, that is both TX and RX. So TX is the data being sent from the client to the server. So I just showed the what state is being maintained on the access point at this point. So at time T2, you receive an ACK number of 2, and that is the received ACK, and there's no previous ACK. Let's say this is the initial state where everything starts. And at time T4, you receive another ACK of 3, and the previous ACK is 2. And at time T6, you see a same acknowledgement as the previous. You can mark it as a duplicate ACK. And at T8, it's the same. So you maintain the same state. And at T6, you see a different ACK number, so that you can so you see that the packet that had been lost is recovered. So you just mark the time as the recovery time. You can also see this as a bad time or wait time of that particular TCP connection. So this is the main core part of the working of the algorithm. It is pretty straightforward, as you can see. Uh, One might ask another question on the same slide, that what about the ACKs being sent from the server? All the ACKs have an ACK number of 1. This is actually expected. There's nothing wrong here because the client is not sending in any data from its side. It is sending all packets with the payload size of 0. So the ACK number 1 is expected. This can be easily determined on the AP using another variable called as expected ACK, that is computed by the sequence number plus the payload size of the packets we receive from the other end. So if you take any packet that is being sent from the client, you see that the sequence number plus the payload size, that is 1 plus 0, is always equal to 1. So whenever a ACK received is same as the expected ACK, you just ignore it, and then you have a check for received ACK and previous ACK to determine if it was a duplicate ACK. So that would be giving you the total recovery time of a particular connection. So at till this point, I was talking about how we can determine the time bad time for a particular TCP connection. But as I mentioned, our goal is to determine the quality of experience of a particular application. And application does not have a single TCP stream. So for example, if you take any application, say you are trying to browse google.com, it fires multiple TCP connections which try to fetch in different types of data. So I've tried to give an example here where the application is using 5 different flows to fetch some data from a server maybe. In this example, I've marked out the burstiness of each TCP flow where the transmission can take place at any time. And I have also marked some recovery events which I marked with red. So how do we get this information on an access point for an application level? Actually, that is pretty straightforward. We can detect the total active time by just keeping track of the last frame time for at least one of the flow for that particular application. So you'd be ending up with something like this, where once you keep track of the last frame time for each flow at an application level, you see something like this. And we also have a mechanism to detect an idle time. So you have to detect you have to be able to differentiate the interpacket gap between a particular flow versus the time spent idle by the user, real idle time spent by the user. So to differentiate that, we have an algorithm where we use a threshold to determine this. So after this, what we do is we have a global view of the recovery time as well. That is, like at least if at least one of the flow is having a bad experience, we mark that the total application is experiencing a bad connection. So if you look at this right now, you have a global view where the blue indicates the total time the application has been actively communicating on the network, while the red part gives you the total time the TCP the application spent in a wait state, or the total bad time. So we'll be using this to map to the user experience. And before going to that, I just mention a small bit here. So if you were wondering how can all this be done on an AP, we actually have already implemented this, and the memory used per application per client is around 0.5 kb to 3 kb, and throughput impact for the whole algorithm running at a very high load is just around 1 to 3%. So this can be done, and so I'll be moving ahead with the results to show how the user's experience can also is also determined by this particular method. So going ahead with the results, we had a very simple test setup where we had a client device which had a browser running. That browser made queries to google.com, and the client was connected to one of our access point where this one of our access point, and it was running to the server. So from the browser, we collected the page load time, and from the access point, we took a packet capture, and access point we took a packet capture, and through when we were doing the POC, we just varied the network conditions of the network device, where we changed the bandwidth and the induced packet loss using a traffic shaper tool. So the results look something like this. In the first variation, we changed the bandwidth from 3 kbps to 50 kbps. So 3 kbps is pretty low. One single point I forgot to mention here. So the browser we were collecting the page load time. So our idea was to estimate the user's quality of experience. And one simple way to do that was to compare our results, what we get from this packet capture, with the user's page load time. So page load time is the amount of time taken for the page to load, which is which signifies what the user actually felt about that application. So going back to this chart, first we check the recovery time versus the bandwidth, and at very low bandwidth, it is expected to have very bad connection because 3 kbps is not something where you can run a web query on. After that, we started comparing the recovery time with the page load time, that is the indicator for the user experience for the same experiment. And we see a direct relationship between the page load time and the recovery time. So as you can see, the page load time increases, so does your recovery time. So from this, you can infer that our recovery time algorithm is indicating the network behavior, or the quality of experience of the user at that particular point of time for that particular application. Similarly, we see similar results in case of induced packet drops, where we vary the packet drops from 0 to 20%, and you can see a significant increase in the amount of recovery time from 0 to 80 seconds as we increase the amount of packet drops to a drastic level. And you see a similar correlation between the page load time and the recovery time here as well, indicating that this method actually works. After this, to have a global view, we ran some experiments where we compared how does this bad time look, how does this method look at an overall connection for a repeated set of experiments, that is loading a page. And we induced 3% packet drop for this particular connection, where you can see the active time plotted on this. This indicates the blue bar which I was showing in the chart earlier, and red indicates the bad time or the wait time for the TCP. And in case of a good connection, the test run really fast because there's no bad connection there, and you can see that the bad time is sitting at 0 because the network and the experience both were pretty good. So this concludes my presentation. I would like to end this with showing this feature in action in our product, which has already been implemented. So here's a small screenshot. So this is a screenshot from our CloudVision Wi-Fi dashboard, where we provide the user an option to select certain applications which he wants to monitor. And for each application, you can see that we are indicating how much percentage of good and bad that particular application has been facing. You see that as the users faced poor app experience for 3% of time if you look at LinkedIn. So you give the user a global picture of how the application was performing in your network. And if you want to see client based details, as I was discussing, you can click on any one of those applications and you go to another screen which looks something like this, which gives you a client level information as well. A point of interest is only these two columns, which is the one on the right is the usage time for that application, and the one on the left is the application experience. So for the first client, you can see that it used the application for 2 minutes and 22 seconds, and you can approximately estimate how much bad percentage it faced. And if you just hover over this, you will also see the actual percentage of bad time faced by this. So that concludes my presentation, and thank you everyone. If there are any questions from
Yeah, thanks, Rikith. We do have some questions. Again, anybody else who wants to ask questions, please type it on the chat window. So the first question is from Sheila. So question is, what if the ACK from the client gets lost before reaching the server? Is there a limit on the waiting time from the server side before starting a new window?
So there are two cases here. So just take going back to my example. So say in the first case, like one of your ACK is lost from the client side. So say any ACK is lost, and it's a perfectly good connection. Let's say there are no duplicate ACKs. If the ACK is lost, the subsequent ACK will be sending an incremented ACK number, which will also ACK for the previous packet that was lost. So in case this third ACK was 4 instead of 3 and the packet was not lost, and say the second acknowledgement from the client was lost, on receiving an ACK number of 4 from the client, the server can infer that even the second packet has been received by the client. Like the subsequent ACK will also ACK the previous data that has been received. And the second part, so how much time does the server wait? So in case this packet has been lost and there's no way for the server to infer from the next ACK packet, that is, it does not have any next ACK packet to infer that that packet has been received, it waits for a certain TCP timeout, and then it retransmits the packet. So that TCP timeout starts off with a certain number. I don't remember the exact number right now, but it has an exponential increase. Like there's a back off period. Like each time the packet retransmission fails, it just increments the wait time and then retransmits again. Did that answer the question?
Yeah, we'll wait for Sheila to respond. So the next question is Balram asks, how would an AP detect and differentiate applications? For example, normal HTTPS browsing versus HTTPS Hangout call. Is there DPI involved?
So we use an external tool for this. I cannot go into more because it's proprietary information. So,
okay.
So,
yeah. Joy Curry asks this question, for voice video conferencing applications, is TCP involved? If not, then how would one assess QoE for such applications?
So yes, for voice and video conferencing applications, you see TCP connections as well. So the way we do that is, in case you get a VoIP or a video conferencing call, we just run the first algorithm which I introduced earlier. And in case it's not a VoIP or video conferencing call, only then we'll be falling back to this particular algorithm. So all voice and video conferencing applications go through that first method I discussed.
Okay. Anurag Kumar asks this question, what is the source of errors in the study? Are the packet losses induced due to buffer overflow or link errors? Why not just measure TCP throughput for each application?
Can you come again?
Yeah, so let me maybe go step by step. What is the source of errors in the study?
So the source of errors in the study is a traffic shaper tool that is called TC, which can induce packet drops. So these are artificially induced packet drops. And the second source was reducing the amount of bandwidth we are using for giving for that particular user. So if you reduce the bandwidth, you'll see eventual packet losses in your network.
And then the follow-up two questions are the packet losses induced due to buffer overflow or link errors?
So, so in our experiments, the packet losses were induced due to change in network conditions. So these are artificially induced packet losses. But in any network conditions, you can have normal packet losses. So the algorithm works there as well.
And the last question from Anurag is why not just measure TCP throughput for each application?
So if you take an example for google.com, say you open the browser, you search for something and wait for 5 minutes and search for something else, what would be the throughput? Like you have a huge gap and you just did 2 clicks, compared to you are browsing a YouTube video where you have a continuous flow of packets. So the throughput in the throughput in case of YouTube is very high and google.com is very low. So even if you did not have bad connection for TCP for google.com, you'd be like making wrong inferences. Like throughput is not the parameter which you can use at this point.
Okay.
Because the traffic nature is busty.
Suja has the following question. Is this experiment run on AP offering services at full bandwidth, say 25 users at 100 Mbps rate? What do you think are the implications when we inspect each packet?
So we have done this stress testing for this particular thing, and we have used around 100 clients measuring 25 different applications as well, and it does not cause significant impact like compared to our already existing feature. So as I mentioned, it's just around 1 to 2%. Like there's an existing feature over that the throughput impact is just 1 to 3%.
And our final question for you from Ganeshan. A TCP window size is a dynamic number. If packet loss is there, TCP window size will be reduced. It can compute the time lost. How did you take care of this issue? I think there might be a small typo, but still, as long as you get the question, we'll go ahead.
So our idea is to just approximately estimate the amount of waiting time. So if it reduces the window size, yes, it can reduce the window size and send like less packets. So so one limitation of this particular algorithm is we cannot detect delays. So in that case, the delay will be more. So because your window size will get reduced, and the number of packets you'll be sending will be less. But that's a rare case where like you have a very small window size and the delays are too much. However, there's the limitation where you cannot detect delays for this particular method.
Okay, so thanks, Rikith. Thanks for your nice presentation and your patience in answering all the questions.